Testing, testing. All right. States participant. Testing, testing. All right. All right. Greetings, scholars. Let me see. I hope everyone had a great weekend. We're in the home stretch. Let me pull up a calendar real quick. So, a tentative schedule for the remaining sessions. So today we'll work on section 3.1, exponential functions. And then on Wednesday, we'll go ahead and do the last set of the material, which will be section 6.4, systems of equations in two variables. And then from there, that'll leave us 3 days to review for the final. All right. So then on Monday, the 25th, I will focus on exam 1, everything pertaining to exam 1. The rest of that week we'll have off for the holiday. So we'll meet on Monday and then we'll be off for the rest of the week. And then we'll come back on that Monday, December 2nd, and we'll work on exam 2. And then that Wednesday, hang on. That Wednesday, December 4th, we'll focus on exam 3 and those additional 2 sections, 3.1 and 6.4. So Wednesday, December 4th is going to be the last day of class. That Thursday and Friday, which is December 5th and 6th, is going to be the reading period. So I think the school is closed, and that's just an opportunity for you all to prepare for your finals. And then that second full week of December, December 9th to the 13th is the final exam week. More than likely, I'll be hosting your finals, so you can expect our final to become available on that Sunday, December 8th at 11 a.m. And you can access it up until that Friday, December 13th. Friday, December 13th is going to be the hard deadline for all assignments, right? So everything is due that day. Idealistically, you want to have completed all of your assignments so that when you submit your final exam, that's the last idealistically, you want that to be the last thing that you submit. So when you submit your final, you should be done. In preparation for the final, if you're going back and submitted either older assignments or boosting your overall score, my recommendation is to prioritize your exams first. That's where you're going to get the most bang for your buck. All right. So that has the heavier weight. And then I would encourage you to prioritize the homework last, where that's going to be a lot of work for minimal points. Okay. As usual, if you have questions, feel free to unmute yourself to get my attention or type in the chat or the Q&A and we can talk about it. Otherwise, we're just going to go ahead and get the party started. I think I'm going to have to make my podium today. Just ate breakfast, brunch. I guess it'll be brunch at this point. Oh, so I'm battling the itis. It's so weird. Like this time of day is just a little bit challenging for me. Like I realize that this is when I tend to take my naps, whether I eat something or not. I just put on a movie or something and just drift off to La La Land for a few hours. That's just how I naturally am around this time of day. Getting younger, older, who knows? Who cares? Okay, all right. That's part of life. You just roll with the punches and keep it moving. Okay, so let's see. Yep, I gotta reboot you because you are not behaving. So it's right here. Okay, that's better. Guess I'll grab this one. All right. So okay. So we'll be moving into chapter 3. Chapter 3 focuses on exponential and logarithmic functions. We're only going to be working on section 3.1 from this chapter. 3.1 covers exponential functions. So a few objectives here. 1, define an exponential function. 2, graph exponential functions. 3, develop formulas for simple and compound interest. 4, and understand the number e. 5, graph the natural exponential function. And 6, model with exponential functions. Okay. So an exponential function is a function f of the form f of x equals a to the power of x, where a is strictly positive and not equal to 1. We call this an exponential function with base a and exponent x. And the domain of the exponential function is all reals, right? So in the past, you may have seen like power functions, things like x squared, 7x to the 4, 10x, whatever to the power of 3, stuff like that, where the variable was the base of the exponent and we had different powers. So here, now they're going to kind of reverse roles. Now our base is going to be a positive number that's not equal to 1, and now our variable's in the exponent, all right? And so we're going to explore just how that unfolds. In this example, this is evaluating exponential. I'm going to leave this as an exercise. If you need to see this worked out, this is in my recording. I feel like it's not too terribly bad, too terribly difficult to grasp these concepts. So that's the only reason I'm skipping it. But again, if you want to see it worked out, you can use my recordings or you can use this slide as well. If you're not going to use the recording, I would still encourage you to try these out yourself and generate your own answers first, and then use the next slide to just compare and contrast. And you want to make sure that you can generate the right results here, okay? So in this example, we're asked to graph this exponential function, f of x equals 3 to the power of x. So the way we're going to introduce graphing here, we're going to make a table of values, choose several values of x and find the corresponding y. So essentially what we did here, we let x be -3, -2, -1, 0, 1, 2, and 3, okay? And then we calculated the corresponding y's. So in this instance, it's probably easier if we kind of work backwards, like starting with 3. So when x is 3, 3 to the power of 3 means 3 times 3 times 3, which is 27. And then when x is 2, we have 3 squared, so that result is 9. When x is 1, we have 3 to the power of 1, which is 3. When x is 0, 3 to the power of 0 is 1. When x is -1, so a negative exponent, all right? A negative exponent means what? It flips. It becomes a fraction. So if we have 3 to the power of -1, that's really 1 over 3, all right? So it flips. A negative exponent means the base flips as a fraction, okay? So then 3 to the -2 is really 1 over 3 squared, which is 1 over 9. 3 to the -3 is 1 over 3 cubed, which is 1 over 27. So now we have our table of values. We have our x values with their corresponding y values. So then we will plot the points and we'll get an image like the following. Okay. So when we plot the points, we get something like this. This image on the right-hand side, that's the general shape of an exponential, right? So with minimal to no manipulations, that's going to be the general shape of our exponentials. Notice that the x-axis serves as a horizontal asymptote. So in general, exponential functions have a horizontal asymptote. As we go up to the far left, as x goes to the far left, y gets infinitesimally close to 0. As we go up to the far right, y tends to infinity. So as x goes to infinity, y tends to infinity. With exponential functions, we have a horizontal asymptote, namely the x-axis, as long as we don't do any manipulation or transformations. There's no vertical asymptote, right? So the domain for exponentials is all real, meaning that every x is accounted for. For every x on the real number line, we can find the corresponding y. Okay. So the domain in this case, the possible values that x can take on is going to be all reals. Take a moment to yourself. What do you think is the range of this guy? If the domain is the very bottom to the, if the domain is the very left to the very right, then just to yourself for a moment, what do you think is the range in this instance? Man, this itis is like no joke. All right, so the range, if the domain is the very left to the very right, then the range is going to be the very bottom to the very top. That's fine. So how far down does this graph go? It goes down to y equals 0 and up to y equals infinity, or up to infinity. But the zero is going to get a parentheses, and it's going to be the open interval from 0 to infinity. In other words, what we're saying is this function gets infinitesimally close to y equals 0, but it doesn't actually reach y equals 0 unless we do some transformations or manipulations. Okay, so a little bit of chatter. And also this image, we call this exponential growth. So as we trace it from the left to the right, it's constantly increasing. Okay, this is where the base of the exponent was larger than 1. Okay, so in this next example, we're going to look at when the base is between 0 and 1, right? So we can graph this in a similar fashion where we choose several values of x and find the corresponding y. So we can let x be, -3, -2, -1, 0, 1, 2, and 3, and find the corresponding y values. In this instance, it's probably easier to go just in the normal direction. So when x is -3, again, a negative exponent means you flip the fraction. So 1/2 to the power of -3 flips and becomes 2 to the power of 3, which is 8. 1/2 to the power of -2 flips and becomes 2 squared, which is 4. 1/2 to the -1 flips and becomes 2 to the power of 1, which is 2. 1/2 to the power of 0 is 1. 1/2 to the power of 1 is itself. 1/2 squared is a quarter. And 1/2 cubed is an eighth. Okay, so we get this table of ordered pairs, and we plot our points, and we get an image like this. Right, so the previous image that we had, we call the exponential growth. Again, as we trace it from left to the right, it's constantly increasing. We will call this image exponential decay. So as we trace it from the left to the right, it's constantly decreasing. Okay, but notice that the domain is the same, all reals. And the range in this case is the same as well, from 0 to infinity. Okay, so now we have a slightly more formal articulation of some properties of exponential functions. So let f of x equal a to the x, where a is strictly positive and not equal to 1. Then the domain of the exponential function is going to be all reals. The range of the exponential function is going to be the open interval from 0 to infinity. Again, we use parentheses on the 0 because we get infinitesimally close to 0, but we don't actually reach the 0. The entire graph of the exponential function lies above the x-axis. Again, the x-axis serves as a horizontal asymptote. Since f of x plus 1 over f of x equals a to the power of x plus 1 over a to the x, but that's the same as a to the x times a over a to the x, which boils down to just a. So then what this is saying is that for each unit increase in x, our y values increase by a factor of a. So every time x increases by 1, our y value increases by a factor of a. So then as long as a is larger than 1, then the growth factor is going to be a. Because the y value is going to increase by a factor of a for each unit increase in x. F is so the exponential function is going to be an increasing function. So as we trace the graph from the left to the right, it's going to rise or go up. As x goes off to the far right, y it tends to infinity. As x goes off to the far left, y tends to 0. Okay, we got a few more, and then we'll summarize. So then, if the base of our exponent is between 0 and 1, then we're going to call this, the decay factor is going to be a. So because the y value decreases by a factor of a for each unit increase in x. When the base is between 0 and 1, the exponential function is going to be a decreasing function. So as we trace the graph from the left to the right, it's going to fall. As x goes to the far left, y tends to infinity. As x goes to the far right, y tends to 0. Okay, and then each exponential function is 1 to 1. Let me make this statement when it comes to 1 to 1. So the following 4 statements can be used interchangeably. A function is 1 to 1, but that's the same as the graph passes the horizontal line test, but that's the same as every y corresponds to exactly 1x, but that's the same as the function has an inverse. So those 4 statements, again, we can use them interchangeably. So whenever we say 1, we automatically mean the other 3 as well. Let me say them one more time. So a function is 1 to 1 is the same as The graph passes the horizontal line test, but that's the same as every y corresponds to exactly 1x, but that's the same as the function has an inverse. Okay, so those statements we use interchangeably. Okay, so then algebraically, how do we show that a function is one-to-one? Basically, if we evaluate f of m, if we set two distinct y values equal to each other, then we need to show that the x value, two distinct x values have to be the same. Right? In other words, if we evaluate f of m, or we can do, I'll match this. So if we did f of m equals f of n, and then we simplify, we need to show that m equals n, right? So if we start with f of m equal to f of n, and we finish with m is not equal to n, then it's not one-to-one, right? So, that will come out in the homework, and we'll get to, that's going to be easier to see when you're working an example. But that's, again, algebraically, that's called the uniqueness proof, and that's algebraically how we show a function is one-to-one. But if we start with the left and we don't finish with the right, then it's not one. Okay, and then we mentioned a moment ago that this also means that f has an inverse. A few more. So the graph of an exponential has no x-intercepts, so it never crosses the x-axis. No value of x will cause f of x to equal 0. The graph of f of x is a smooth and continuous curve and passes through these three critical points, namely when x is -1, 0, and 1. Those three critical points, they basically kind of like give you the general shape of your function, your exponential. Whether you have exponential growth or exponential decay. It just kind of comes in handy when like graphing exponentials. From 4.3 and 5.3, we conclude that the x-axis is a horizontal asymptote for every exponential function of the form f of x equals a to the x. And the graph of y equals a to the negative x is the reflection about the y-axis of the graph of y equals a to the x, right? So if we start with an exponential function and replace x with negative x, that's a transformation, right? So it's similar to like how multiplying the inside by a negative, so it's going to flip the graph horizontally. So instead of having exponential growth, it would flip and become exponential decay. Similar to the second image that we saw just a few moments ago. Okay, so let's pause for the cause for just a moment. I feel like again, those are just properties. I feel like they come out naturally as we kind of work examples. So you don't have to like sit and like commit this to memory. I just wanted to kind of bring this to your attention. And I feel like these naturally come out as we work examples. Okay. So then a few definitions. The interest rate is the percent charged for the use of the principal for a given period. The interest rate denoted by R is expressed as a decimal. Unless stated otherwise, the period is assumed to be 1 year. That is, R is an annual rate. The amount of interest computed only on the principal is called simple interest, right? So simple interest is the lowest form of interest that we have. As you see here, it should be the interest equals PRT, I equals PRT. So the interest equals the principal times the rate times the time. Again, this is the lowest form of interest that we have. The simple interest I on a principal P at a rate R expressed as a decimal per year for T years is given by this, okay? So if you have a formula sheet, this is a great formula to include on your formula sheet. Again, this is a simple interest formula, the lowest form of interest that we have. So Juanita has deposited $8,000 into a bank account for 5 years at a simple interest rate of 6%. How much interest will she receive, and how much money will be in her account at the end of 5 years? Okay. I'm just not that big. Okay, where's my? Okay. Let me see. Simple interest, right? Okay. So again, one of my mentors will say every time you use a formula, write it down. So let's see. Simple interest, the principal times the rate times the time. Okay. So then for part A, interest, the principal is $8,000. the rate is 6%. Okay, let me mention this. So then 6%. Again, we need to write that as a decimal. So the percent symbol, you can look at that as per 100. Okay. So then 6, this is basically saying 6 divided by 100. So we move the decimal to the left 2 spaces. Okay. So 6% as a decimal will be 0.06. Again, the percent symbol, you can look at it as meaning per 100, which means we're going to divide by 100, move the decimal to the left 2 spaces. So again, the rate, 6% as a decimal, is going to be 0.06, and the time for 5 years. Okay. 5 times 6, let me see. So this one's like 1,000.01. 5 times 6 is 30, so there's an extra 10 there. 3 times 8 is 24. And then 1, 2, 3, 4, like that. Backspace by 2. Okay. $2,400. So after 5 years, how much interest does she earn? $22,400. Okay, we'll work on part B in just a moment. I want to kind of share something with y'all, but I don't know how to articulate it. So again, something I came across on YouTube about different ways to become a millionaire. And like, I came across this guy that I guess he was pushing compound interest, which I still believe in. And he was like, I guess he with the presentation that he went into, he started talking about like dividend stocks. And he had like all these techniques. The presentation was like about 2 or 3 hours long. It was kind of long, but one of the cases was like, okay, if you had a dividend stock with the company that's like established, low risk, it's stable, stuff like that. And then he was like, if you can invest maybe $200 a month every month for like 30 years, right? And any money that's earned on the dividend stock, you just feed it back onto itself. He was like, by the end of the 30 years, if you set it up properly and if you're successful, like some of those monthly returns, like from the companies, were like $20,000 a month after 30 years. So I'm assuming that you guys are like somewhere in the range of maybe your early 20s, right? So then 30 years, you could retire at 50, a millionaire. Not, again, I'm no financial advisor, so you would have to like consult a professional. But that doesn't mean that you can't look into it. I'm just trying to bring it to your attention so that you can follow up on it and see if you can create it, right? And so $200 a month isn't too terribly bad as far as an investment, but that was the structure. $200 a month every month for 30 years into a dividend stock, and you reinvest any proceeds earned. So then, if you're like in your 20s, by the time you get to your 50s, you could retire a millionaire, and like you can have like $20,000 a month or more coming in with that same account. And as long as you don't spend more than $20,000 a month, which isn't that difficult to do, you know, um, you'll have money as long as that account and that company is going strong and that account is open. You'll have money forever. And then, what you could do with that account is leave it to your loved ones. And like, I'm of the mindset, I kind of struggle though, because it's like, I want to teach my loved ones to do it, but I won't know by the time I know if it's going to work, it's going to be late. So I don't know the only way I can teach them along the way is if they just took a risk and just tried, like did their own research and just tried along with this. Because it's like I feel like when you have money, it's important that people in your circle have money too. Because if you're the only one to have money, then they're going to be coming after you in some form or fashion, right? And that's like a long term something. Obviously, you can be working on other things along the way, but again, $200 a month. Again, and when I think about it, I spend Lord knows how much on just crap, video games and movies and just crap, stuff that ain't really serving me. It's just really a waste of money. So I could take a fraction of that money that I play with every month and invest it into myself. And then, like, I'm getting up there, but I got to take some kind of action. So at some point, I have the option to retire if I wanted to. But I'm weird. I kind of live like I'm retired already anyway. It don't really cost me much to do much of what I do. And when I want to do something, I just find a way to get it done. But anyway, it's just something to look into. Again, I'm not a financial advisor. You would definitely want to consult a professional to look into it, ask questions, dig, and see what you can get into. Um, and then that's just like dividend stocks. Another one is like real estate. That's another one that I like to look into. Forex trading. And you don't have to be wealthy to start, but you do have to start to become wealthy. Anyway, again, just something interesting, kind of along these lines, something to look into. Okay. All right. So then back to part B. How much money will be in her account at the end of 5 years? So if she started with 8,000 and she's earned 2,400, so then the future amount is going to be her starting amount plus the interest earned, which is the 8,000 plus 2,400 to give 10,400. My dog is having the time of her life over there. I don't know what she's doing, chasing her tail. She needs like some another dog to play with this thing, to run around and chase. Anywho, what time is it? Okay. All right, so not too bad. All right, so we did an example on simple interest. This is compound interest, but I'm going to bypass this one because this is compounded annually. This is a derivative of one that we're going to be using, so I'm going to bypass this one. Again, you can see this example in my recording, and I want to actually get to this one. The one that we saw before was a subset or a derivative of this guy. So I'd rather just put our energy on this compound interest formula. The two formulas are the same. I'll mention the difference momentarily. So with the compound interest formula, what you see here, our A is our future amount after T years. P is our principal or starting amount. R is the annual interest rate expressed as a decimal. N is the number of times the interest is compounding per year, right? So in that previous slide, in the previous formula that we skipped, the interest is applied once per year. So our N would be 1 in that case. All right. But in the more general sense, we might apply it 3 times a year, 5 times a year, stuff like that, right? So that's where we have these variable N. The N stands for the number of compoundings per year, and then T is the total number of years. Okay. So if $100 is deposited into a bank account that pays 5% annual interest, we're asked to find the future value A after 1 year if the interest is compounded annually, semi-annually, quarterly, monthly, and daily. Okay. So we're doing compound interest, right? So let's use the right formula. So again, if you have a formula sheet, this is another great formula to update it with. P times 1 plus R over N to the power of NT. That's our compound interest formula. Okay. So then for part A, if the interest is compounded annually, that means our N is 1. For part 2, if it's semi-annually, that means our N is 2. For part 3, if it's quarterly, that means our N is what? 4. If it's monthly, our N is 12. And if it's daily, our N is 365. Okay. So what I'm going to do, I'm going to use my trusty dusty rusty calculator. The only thing that's changing in each of these instances is N. So I'm going to let that be my variable. So right here. I gotta wait for it to finish whatever it's doing. Okay, thank you. All right. I think I already have it in here. So the principal is 100. the rate is 5% as a decimal is 0.05. N is what's changing in each case, so I put that in as X. And each of these are calculated after 1 year. Let me kind of write those notes. So again, the principal is $100. The rate is 5% as a decimal, 0.05. And the time is 1 year. Okay. So again, I put all of those into my equation editor. All right. And then I want to evaluate it for the different values of y. I mean, different values of x. I could hear it. Nope. Okay. So on the first one, we're going to let our compoundings be once per year. And so then at the end of the year, we'll have $105. So now, if we compounded it twice per year, it's a little bit more, 105.06. And then if we did the compoundings 4 times a year or quarterly, I don't know what I'm writing, 105.09. And then if it's monthly, 105.12. And then if it's daily, 105.13. Okay. So you should notice something. The more compoundings we do, right? You should be able to infer something based on the more compoundings we do in a year. Okay. And just here's a type version of what we just experienced. So now in the previous example, we did multiple compoundings per year. We did once a year, twice a year, 4 times a year, 12 times a year, every day, right? So we're doing more and more compoundings per year. So then we're like, well, what's the limit? What if we were just always applying the interest? What's the limit? That's where this guy comes in. This is our continuous compound interest formula. So whenever you see the word continuous, you want to use this guy here. If you have a formula sheet, you definitely want to add this guy to your formula sheet. The way I remember this guy is the PERT formula, A equals P e to the RT. And I use that whenever we're working with continuous compound interest. So then our A is the amount after t years. Now, again, with these formulas, I don't really expect you to commit them to memory. I just want you to know when to use the proper formula, when to use each formula, right? So different instances call for different ones. The real thing is I just want you to know when to use the proper one. Our A in this instance is going to be the amount after t years. P is the principal, so the starting amount. E is a function in the calculator. Okay. It's kind of like pi. E is like 2.731, yada, yada, yada. It's a function in the calculator. R is the annual interest rate expressed as a decimal, and T is the number of years. Okay. Oh. Okay. So here we're asked to find the amount when the principal of 8,300 is invested at 7.5% annual rate of interest compounded continuously for 8 years and 3 months. Okay. So there's that word continuous compound interest again. So that means we need to use the PERT formula. A equals P e to the RT. Okay. What it asks us to find the future amount. So we're trying to solve for A. We're starting. So our principal is 8,300. The rate as a decimal, 0.075. And the time, it says 8 years and 3 months. So this whole thing needs to be in years. So that 3 months, we need to convert to years. All right. So then 3 months out of 12, 3 divided by 12 is what? A quarter. So 0.25. So then it should be 8.25 years. Okay. I'm going to rearrange this just a little bit. Okay. So then our future amount after 5 years, 8,300 times e to the power of 0.075 times 8.25. I think I might still have it saved if I keep backing up. With that one. 8,300 times e to the power of 0.075 times 8.25. So after 8.25 years, oh, this right here should be, that's really supposed to be 8.25. $15, $4.09, and 83 cents. It's such a beautiful day outside. I was out there earlier. That's another reason why energy is so low. I did some yard work, and I guess I just haven't recovered. And I still need to kind of get back out there, but I don't know if I'm gonna have the energy after I get done with my next group. So anywho, okay, 15,409.83. Okay. So then the natural exponential function, f of x equals e to the x with the base e is so prevalent in the sciences that it's often referred to as the exponential function or the natural exponential function. E comes from like, there's a limit definition as n goes to infinity in calculus. It basically collapses to this number. And then in calculus, there's this concept called the derivative, which is the slope of the tangent line at a point. The reason that E is so unique is that E is like the only function that's its own derivative. So when we take the derivative of E, we get back itself, right? So the slope of the tangent line at any point is going to be that number, right? It's a unique number, right? So you don't need to worry about all that. For our purposes, we just need to know. We just want to use the function. Again, that's the function in the calculator, right? So I think earlier we said that it's approximately like 2.7 something. So here in blue we have the graph of 2 to the power x, and in green we have 3 to the power x. So notice that E is between the blue and the green, but closer to the green. So it's approximately, it's almost 3. It's like 2.7 something. Okay. And then if we wanted to graph these using transformations, we would start with the general shape of the exponential. We have two transformations at play here. We subtracted 1 on the inside of the base function, and we added 2 on the outside of the base function. So subtracting 1 on the inside will move the graph to the right by 1, and then the +2 moves it up by 2. Okay. And then this is an application of exponential function. This is really the PERT formula. It's just extended to be more general. Instead of just talking about money, it's applied to other systems. So then A of t equals A naught e to the kt, where A of t is the future value amount, A naught is the starting amount, and then k is the growth rate, and then t is the time. Okay. All right. So we're essentially out of time. I'm going to go ahead and stop here. But these last couple of examples, I do have them in my recording, so I'm going to piggyback off of those. If there aren't any burning questions, we're going to go ahead and end the session here. Let me think real quick. So on Wednesday, we'll work on the last of the new material is going to be section 6.4, system of equations in two variables. Let me open the floor one more time. Are there any questions, any burning questions before we go our separate ways? Going once, going twice. Let me check the chat real quick. Okay. So again, yeah, if there aren't any burning questions, we're actually going to go ahead and end the session here. And we'll meet back on Wednesday to kind of go through the last of the new material. And otherwise, gentlemen, enjoy the rest of your evening. Take care. Peace. I'll go ahead and make a copy of this available. My bad, guys. I'm here. Let me. Let's go in. Share my screen. Start the broadcast. A few more minutes. Yeah. I don't know. Just lost track of time. Okay. Right here. Here. Siri, turn the heater off. Yeah, I think I was just tired. My alarm went off. I was like, "What time is it?" She was like, "It's 2:58." I was like, "Okay, I'm getting up." And then I blinked my eyes. I was like, "Oh, what time is it?" It's 3:11. I was like, "Oh my god!" Just over stuff. I was just, I was just tired. I guess, like I said, literally, I just blinked my eyes and lost 10 minutes. So I was like, "Okay, well, we're here now." So, let me do this right here. Okay, and then like this single page. All right, gentlemen. Let's bring up a calendar. Okay. All right. So, welcome, gentlemen. I hope everyone had a great weekend. Sorry for again the delay. It just, accidentally lost track of time. So let me see. So today we're going to be working on. So I think exam three was just due maybe 15 minutes ago, give or take. Um, so we only have two sections remaining as far as new content. So today we'll work on section 3.1 exponential functions. And on Wednesday, normally we do the corresponding homework. We're going to go ahead and do the final, the last in the new material on Wednesday. So that'll be section 6.4, system of equations in two variables. And then next week on Monday, so then that'll leave us 3 days to review for the final. So we'll focus on exam one this upcoming Monday, 11 on Monday, and then for the rest of that week we're off for the Thanksgiving holiday, so we'll be out for almost for a week, and then we'll come back the following Monday, which will be December 2nd, and we'll focus on exam two, and then at Wednesday, December 4th, we'll focus on exam three with the two additional sections, 3.1 and 6.4. The December 4th, that Wednesday, December 4th, is the last day of class, and that'll be the last of our meeting sessions. That Thursday and Friday, December 5th and the 6th, is the reading period, so I think the school is closed that day. And then our final exam week is that second full week of December, which is December 9th through the 13th. So more than likely, I'll be hosting your final. So you can expect it to become available on that Sunday, December 8th at 11 a.m. And then you can access it for 5 days up until that Friday, December 13th. That Friday, December 13th serves as the hard deadline for all assignments. Okay. So idealistically, as we approach the final, you wanna have everything turned in and submitted and ready to go. So that way when you take your final exam, you're done. Right? The final exam should be the last thing that you do. Okay. So you don't want to like finish the final and then have all these lingering assignments. Also, I would encourage everyone, like you can keep in mind that you can boost your overall score. Like you can go back and improve scores. If you are trying to boost your overall score, I would encourage each of you to prioritize your exams first. That's where you're going to get the most bang for your bucks. So, and then once your exams are where you'd like them to be, like if you've made less than a 90% or maybe 95, um, you know, go back and redo them. You get unlimited attempts. The system is only going to take your highest score, so you have nothing to lose and everything to gain. And then once your exams are where you'd like them to be, then I would encourage you to like prioritize the homework last. The homework is going to be a lot of work for minimal points. Okay, you're not going to really see the grade move much with the homework. Let me look around here. Okay, and so that's pretty much a snapshot of our remaining sessions. Sorry, I always struggle around this hour. I don't know why. Like, I guess I'm just getting older. Like this hour, I just always want to take a nap. Now, part of it is the itis. I did kind of eat like a brunch right before my 2 o'clock, and I guess I just never got my energy back. But anywho, we must press forward. There we go. Okay. All right. So let me see. We're gonna let's go ahead and start here. All right. So today we're working on chapter 3, which was section 3.1, exponential functions. So again, this is going to be the only section that we work on in chapter 3 for this course. And a few objectives here. So one, define an exponential function. 2, graph exponential functions. 3, develop formulas for simple and compound interest. 4, understand the number e. 5, graph the natural exponential function. And 6, model with exponential functions. Okay, so a function f of the form f of x equals a to the power of x, where a is positive and not equal to 1, is called an exponential function with base a and exponent x, and the domain is all reals. So in the past, we've worked on expressions like x squared, 5x to the power of 10, where our variable is the base and it raises some power. So now we're going to kind of switch those roles where the base is now a positive number not equal to 1. And now our variable moves up to the exponent. Okay? So we're going to be exploring concepts and different things that unfold from that. So this first example is on evaluating exponential functions. I'm going to leave this as an exercise. If you need to see these details worked out, I'm going to refer you to my recording. I feel like this isn't too terribly bad, so that's the only reason I'm skipping it. I feel like you can kind of get that one. I would encourage each of you to attempt these on your own at first. Take them as far as you can. Generate your own results. You can use the next slide to compare and contrast. And then if you need the details, these are in my recording. Okay. So then here we're asked to graph the exponential function. Let me see. So to graph this, we would create a table of points. This is one way we have going about it. We would choose several values of x and then find the corresponding y. So we would like x be -3, -2, -1, 0, 1, 2, and 3. And then we will find the corresponding y. So in this instance, it actually might be easier to kind of work backwards. So if we start with 3, right? If we start with 3, when x is 3, 3 to the power of 3 is going to be 3 times 3 times 3, which is 27. 3 squared is 9. And then 3 to the power of 1 is 3. Sorry. 3 to the power of 0 is 1. And then 3 to the power of -1, right? A negative exponent causes the base to flip, right? So 3 to the power of -1 is the same as 1 over 3. 3 to the power of -2 is the same as 1 over 3 to the power of 2. So it's 1 over 9. And then 3 to the power of -3 is 1 over 3 to the third, which is 1 over 27. Okay. So then with those ordered pairs, when we plot the points, we get an image like this on the right. And the image on the right is the general shape of an exponential function, right? So that's the general shape. I noticed that as x goes off to positive infinity, or x goes off to the far right, y tends to positive infinity. And as x goes to negative infinity, or in other words, as x goes to the far left, y tends to 0. So here, the x-axis serves as a horizontal asymptote. So as we go up to the far left, the graph gets infinitesimally close to 0, but it doesn't actually reach 0. Not without any transformation, right? We'd have to manipulate the function or the equation in order for it to cross the x-axis. But in general, without any manipulation, the exponential function lies entirely above the x-axis. Okay. And again, the x-axis serves as a horizontal asymptote. There's no vertical asymptote in this case. I know it might be tempting to think that like, oh, there's a vertical asymptote, but there isn't. So in other words, no matter what x value we choose on the real number line, we can find the corresponding y. Like if x were 5, we could find the corresponding y. It would be 3 to the power of 5, right? If x were 10, we could find the corresponding y. If x were 1,000, we could find the corresponding y, right? So, again, there's no vertical asymptote, so every x is accounted for, but there is a horizontal asymptote. The domain of this guy, the very left to the very right, is all reals. Again, every x is accounted for. And the range, right? The range is going to be the very bottom to the very top. So just take a moment to yourself to think, what do you think is the range of this guy? The very bottom to the very top. How far down does this graph go versus how far up does it go? Hopefully, you're thinking that the range is 0 to infinity, right? The open interval from 0 to infinity, meaning we get infinitesimally close to 0, but we don't actually reach 0 as far as the range is concerned. Okay, I feel like I got my second win. And that was part of it. I was trying to take a nap. Like I had about maybe 15 minutes between classes. And I swear, like, one thing that kind of trips me out, like when we go to sleep, we completely lose track of time. We don't know if it's been like a few minutes, a few hours, a few days, and I'm just like, my mind just starts messing with me. I'm like, well, how do I know I wake up in the same reality? Because technically it is a quote unquote different reality. I don't know. I guess it depends on how you define it, because things are always changing, right? You wake up and something has changed in the day. And then I started thinking about the movie like Groundhog Effect. Like in that movie, I can't even, not Rick Moran. Who was his name? Dang, for whatever reason, I can't think of his name. But in the movie Groundhog Day, the protagonist wakes up and he's reliving the same day over and over and over. And like if you're not like punching a clock or leaving the house, it kind of feels like that with minor changes. Like it really feels like the Groundhog Day. So if you haven't seen that movie, just check it out. It's an old movie from like maybe the 90s or something like that. It's just a little bit trippy, kind of fun movie. But yeah, just thinking about consciousness and going to sleep and dreaming. It's like, how do you know you're not astral projecting and visiting another reality, right? Like, how do we know we're not part of a simulation? And like when we go to sleep, that's just our avatar or our user is like turning the game off, and then we don't really know how much time has passed. I know we have clocks and things that tell us the time, but if we can change clocks and daylight savings, then why can't we change it in another? Like this time about I just be like, thinking like that sometimes. So anyway, it's probably just me waking up. I don't know. Who knows? It's just fun stuff. It's fun. Anyway, I got more I can say on it, but I'm gonna let it be. Okay. So in the previous example, right, I think we chose several values of x, we plotted. That was an example of what we call exponential growth, where the base of the exponent was larger than 1. So now here, the base is between 0 and 1, right? And so we're going to look at this graph. We chose several values of x. We let x be -3, -2, -1, 0, 1, 2, 3. We find the corresponding y. And in this instance, it's probably a little bit easier to go forward. So like if we start with, let x be -3, right? So then 1/2 to the power of -3, the negative causes the fraction to flip. So it's really 2 to the power of 3, which is 8. 1/2 to the power of -2 is 4. 1/2 to the power of -1 is 2. 1/2 to the power of 0 is 1. 1/2 to the power of 1 is itself. 1/2 squared is a quarter. And 1/2 cubed is an eighth. Okay. So now we have our set of ordered pairs. So our x's with the corresponding y's, and we plot the points. And again, in the previous example, we had exponential growth. So this image is what we would call exponential decay. With exponential growth, as we traced it left to right, the graph was always increasing. With this image, as we trace the graph from the left to the right, the graph is always decreasing. We still have the x-axis as our horizontal asymptote, right? And so the domain is all reals, and the range in this case is still 0 to infinity, the open interval from 0 to infinity. It's just that as we trace it left to right, it's decreasing instead of increasing. Okay. So then again, we want to kind of take some time to look at some properties of exponential functions. So let f of x equal a to the x equal a to the power of x, where a is strictly greater than 0 and not equal to 1. We want to consider this exponential function. The domain of this exponential function is going to be all reals. So every x is accounted for on the real number line. For every x, we could find the corresponding y. The range of the exponential function is going to be the open interval from 0 to infinity. In other words, the entire graph lies above the x-axis. We get infinitesimally close to 0 as we go to the far left, but it doesn't actually reach 0. All right, so that's a concept that you have to kind of use your imagination. You know, a way you can kind of, I don't know, for whatever reason, I always want to bring up like Ant-Man, you know, how like he can shrink down to the quantum realm. It's kind of the same thing here. You know, when you're working these examples and, you know, when you look at, like, if you put it in a graphing calculator, it looks like it's touching the line, like it's on 0. But if you actually zoom in, like go into the quantum realm, you'll see that there's actually always space between our graph and the x-axis, provided we don't do any transformations or manipulations, right? So analogous to Ant. How powerful. Like, is there, like, in the MCU universe that anybody in y'all would deem would be like the most powerful hero? Or I keep wanting to say mutant, but they're not all mutants. But like, who would you say is like the most powerful, or like the most like unassuming hero? Like you don't realize how powerful he is until he like decides to turn off his restrictions. Like Spider-Man is like one of those. You know, you don't realize what he can do until he just stops caring. And then if you took like the most powerful in the DC universe, can you put them head to head? Are they like the same? Are they evenly matched? Does one dominate? You know, this is just where my mind goes. I like those analyses. And like one thing that I find, this is just me just yammering. Like in a lot of the games that I play, they all have this like feature where, like for instance, if you take Dragon Ball Z Dokkan Battle, you got like 5 different types of characters, and it's kind of color coded. And I'll just do it like, I think blue is agility, red is strength, orange is like physical, purple is intelligent, green. What is green? I can't think of what the green one is. But basically, blue beats red, red beats orange, orange beats purple, purple beats green, and green beats blue. So it's not really anybody that's stronger. It's just you always have somebody that can counter you, and you have somebody that you have the advantage over. And so a lot of my games have a mechanism like that, right? Every time you think you have the upper hand, well, that character counters you or beats you. So I always think about like incorporating mechanisms like that as well. Anyway, just interesting things. So yeah, back to like the whole Ant-Man thing and zooming in and always finding space between our graph and the x-axis with the horizontal asymptote. Okay. So then more properties, since f of x plus 1 over f of x equals a to the power of x plus 1 over a to the x, but then that's the same as a to the x times a over a to the x, which is essentially just a. So what this is telling us is that the y value changes by a factor of a for each unit increase in x. So every time x increases by 1, the y value increases by a factor of a. So then when a is larger than 1, we call this the growth factor is a. Because the y value is increased by a factor of a for each unit increase in x. F is an increasing function, so the graph rises as we trace it from the left to the right. As x goes off to positive infinity, y goes to positive infinity. As x goes to negative infinity, y tends to 0. And then if the a were between 0 and 1, or essentially less than 1, then the decay factor is going to be a, because the y value is going to decrease by a factor of a for each unit increase in x. This function is going to be a decreasing function, So as we trace the graph from the left to the right, it's going to always be decreasing. As x tends to negative infinity, y goes to positive infinity. As x goes to positive infinity, y tends to 0. Okay. And then for the sixth property, each exponential function is 1 to 1. So they're really, let me kind of say, oh, here, I'll say this. Let me say these side note for right now. So 1 to 1, the following four statements can be used interchangeably. A function is 1 to 1 is the same as the graph passes the horizontal line test, which is the same as every y corresponds to exactly 1x, which is the same as the function has an inverse. So whenever you hear one of those, whenever one of those are true, then you can, all four of those statements mean the same thing, just articulated four different ways, right? So let me kind of say that one more time. A function is 1 to 1 is the same as every y corresponds to exactly 1x, which is the same as the graph passes the horizontal line test, which is the same as the function has an inverse. Again, all four of those statements can be used interchangeably. And then algebraically, to show that a function is 1 to 1, we use something called the uniqueness proof. So if we evaluate f of m equal to f of n, we have two different y values we set them equal to each other, then we need to show that the x values have to be equal to each other, right? So we start with f of m equals f of n, simplify both sides all the way down. If we finish with m equals n, then that means that the function is 1 to 1, right? It's unique or whatever. Versus if we start with f of m equal to f of n and we finish with m not equal to n, then the function is not 1 to 1, right? That I feel like it'd be more clear if we ever come across an example on how to show algebraically whether a function is 1 to 1 or not. Okay, and again, this all means that the function has an inverse, like we said in those four interchangeable statements. The graph of an exponential function has no x-intercept, so it never crosses the x-axis. There's no value of x that will cause the exponential function to equal 0, okay? And then the graph of the exponential function is a smooth and continuous curve and passes through these three key points, namely when x is -1, 0, and 1, right? It passes through those points. And then from 4.3 and 5.3, we conclude that the x-axis is the horizontal asymptote for every exponential function of this form. All right, we said that a few times. And the graph of y equals a to the negative x is the reflection about the y-axis of the graph of y equals a to the x. So if we think about the general shape of exponential, right, starts off infinitesimally close to 0, passes through the point 1, 0, and then grows up to infinity. Well, if we replace x with negative x, that's similar to our transformations where we multiply the inside by a negative. So it causes our image to flip horizontally. So then instead of having exponential growth, we have exponential decay, right? Exponential decay. All right, so, okay. And a few more definitions. So, and then with those previous properties, you don't necessarily have to like commit those to memory or anything. They naturally kind of come out as we work examples. Let me see. Actually, I'm gonna go like this. Okay, cool. Yeah, again, you don't have to sit and like commit it to memory or anything. They tend to naturally come out. I just wanted to kind of expose these properties to you so you're aware of them, and then as you kind of work examples, they naturally kind of sink in. So there was some definitions. It says the interest rate is the percent charged for the use of the principal for a given period. The interest rate denoted by R is expressed as a decimal. Unless stated otherwise, the period is assumed to be 1 year. That is, R is an annual rate. The amount of interest computed only on the principal is called a simple interest. So simple interest is like the lowest form of interest that we have. It's going to be I equals PRT, okay, which we have here. Where I is the interest earned, P is the principal or the starting amount. The rate is the interest earned per pay period, expressed as a decimal, right? So a lot of times we have to convert that to a decimal. And the T is the time in years. Okay, so Anita has deposited $8,000 in a bank account for 5 years. A simple interest rate of 6%. How much would how much interest will she receive, and how much money will be in her account at the end of the 5 years? So it says simple interest rate. So let's use the simple interest formula. Let's see. So we're working on A. I equals PRT. Okay. So let me mention this: the 6%. Right. The percent symbol, you can look at it as per 100. Okay. So then 6 times 1 over 100, or in other words, 6 divided by 100, we move the decimal to the left 2 spaces. So 1, 2. So 6% as a decimal is going to be 0.06. Let me see. The principal, so that's our rate. The principal was 8,000. And the time is 5 years. So our principal was 8,000. The rate as a decimal, 0.06. And the time was 5. Let's see. This is like 1,000. 6 times 5 is a 30. So there's an extra 10 in there. 24. So that, in other words, it's, you can ignore the blue for that part. It's 8,000 times 0.06 times 5 to give us 2,400. So that's the interest earned after the 5 years for this account. And then how much money is going to be in her account after 5 years? So the amount after 5 years is going to be her starting amount plus the interest earned. So that's going to be the 8,000 plus the 2,400 to give her 10,400. Yeah, that nap made a world of difference. Like I felt like I got my energy back. I don't know. I just like crashing. Like I said, I had just eaten brunch essentially right before class, and I guess body's like, nope, we need to shut down for a minute. The itis. And I made it through the first one okay, but the second one, I don't know. I almost overslept, but I made it just in time, so we're here. Okay, I think we got both of these parts. So now this one goes into compound interest. I'm going to skip this one for right now because this is a derivative of the main one that we need. If you want to see these details, again, I'm going to refer you to my recording for this. Same for this example. And I actually want to start here. So this is compound. This is the same formula. It's just that the previous one, the interest was only applied once in a year. This one, the interest can be applied several times in a year, right? So this is our compound interest formula. Again, the previous one was a derivative of this guy. If you let n be 1, then we would get the previous formula. So I felt like it would just make more sense to just focus on this guy. Okay, so this is our compound interest formula. If you have a formula sheet, it is a good idea to update your formula sheet with this guy, where A is their future amount after T years, P is our principal or starting amount, R is the annual interest rate expressed as a decimal, N is the number of compoundings per year, so how many times the interest is applied in a year, and then T is the number of years that this system or account is going for. So let's see, if $100 is deposited in a bank account that pays 5% annual interest, we're asked to find the future value A after 1 year if the interest is compounded with these varying amounts, right? Okay, so compound interest, let's write that formula real quick. So the future amount is going to be P times 1 plus R over N to the power of NT. Okay. So then for number 1, if the interest is applied annually, that means the number of compounds in a year is going to be 1. For 2, if it's semi-annually, that means the number of times the interest is applied is twice in a year. For 3, if it's quarterly, that means n is 4. For 4, if it's monthly, that means n is 12. And for 5, if it's daily, that means our n is 365. Okay. So right here. Okay. So I think I already have this formula in my equation editor. The principal is $100. The rate is 5% as a decimal, 0.05. We have those different values of n, and the time is 1 year. Okay. So my calculator, I basically put everything in, but the only thing that was changing were the n. So I replaced n with x and basically made it a function. Then we can call on that function. So when n is 1, and after 1 year with those conditions, the account's going to have $105 in it. I don't know what I'm writing today. I swear I go through senioritis like every semester. The closer we get to the final, my brain already be shut off half the time. That's why I get excited when I have to think about something. Because I don't really be thinking about this stuff. And then it gets worse. Like as we get closer to like the end of the semester, I just be thinking about like this time of year. My favorite thing to do is like to binge watch the Harry Potter movies. I don't know why I associate Harry Potter with Christmas. I know they have a lot of Christmas scenes, but that's just when I like to watch them. I don't know. Christmas break, I tend to watch that on repeat or stuff like that. So that's what I'd be thinking about half the time around this time of year, and just like trying to get stuff together. Okay, so let's let n be 2. So then we got 105 and 6 cents. And then when n is 4, 9 cents. When n is 12, 12 cents. So 105 and 12 cents. And then when n is 365, and 13. Another thing that's hilarious, my chihuahua's over here snoring like a grown man. She's a little bitty dog. She's just like, it's so funny to me. She'd be oblivious. It'd be so funny. She'd be in her own world. I'd be in my own world, so I ain't even mad at her. Okay? So hopefully this is okay. Oh, shyster. We are out of time. All right, so we got these. Let me just do a quick scan of the remaining items. Continuous compound interest. So you should have noticed something. The more compoundings we did per year, you should notice something about those previous outcomes. So then, now the question is, well, what happens if we're always applying the interest? Like if we apply the interest continuously or nonstop? So then that's where this formula, the continuous compound interest formula, comes into play. A is the future amount, P is the principal, E is a function in the calculator, R is the rate as a decimal, and T is the time of year. So whenever you see the word continuous, you want to use this guy. The way I remember this formula is like PERT. But yeah. And so again, and you also want to add this into your formula sheet if you have one. I don't expect you to memorize these formulas. I just expect you to know which formula to use given whatever the proper situation or proper instance. Gonna have to use my recording for this one. Let's see if there's anything here. And so E, again, is a function in the calculator. It's approximately 2.7 something. So you see in blue, you see the graph of 2 to the x. In green, you see the graph of 3 to the x. Notice that e to the x is between the blue and the green, but fairly close to the green, all right, because it's approximately 2.7 something, okay? Transformations, I'm going to use my recording for this one. It's quick, but I'm going to use my recording because we are out of time. And then, so this is a model. This is an application of the exponential function. It's similar to like PERT. We just kind of changed the labels a bit. And so instead of talking about finances, this is like generalized into other systems like population growth, bacterial growth, other types of systems. So you definitely want to check out my recordings on these guys. They're not too terribly bad, I don't think. I don't feel like they're too terribly bad, but you definitely want to check them out. Are there any burning questions before we go our separate ways? Uh, Let me see. So this upcoming Wednesday again is going to be the last of our new material. I know we have a lab component with this, so just be sure that hopefully I mean it's kind of too late if you haven't been doing it by now, but just be sure that you've been in communication with my colleague Dr. Lamar. She coordinates the lab component. Again, her portion is worth 10% of her overall grade. And we'll meet back on Wednesday to go over the last of the new material. If there aren't any burning questions, we're actually going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of your evening. And I'll see you all Wednesday, same time, same place for the next installment. Take care, gentlemen. Peace. 4, I got 3 hours. Go ahead and make a copy of this available. Share. Let's go. Let's go. Box. Phone. Additional. Let's go. Notes. Updated daily. Right there. And upload. All right, guys. And I'm going to go ahead and do your attendance. All right. Take care. Is there a question? Do you have a question?